We're going to be talking about control flow today, guys. Just to introduce myself, hi, I am Sam Abrahams. I'm a co-author of TensorFlow for Machine Intelligence. I teach deep learning with TensorFlow at Metis downtown. I'm a longtime TensorFlow contributor, and some of you may know me as the TensorFlow and Raspberry Pi guy, who isn't Pete Worden, a wonderful guy at Google. And if you guys are interested, I have the PDF slides as well as a notebook for code related to this talk online here. It's rather long, but if you get to github/samjabrahams/talks, there's only one thing there right now because I'm migrating my talks into this repo to centralize it. Just to quickly look at the notebook, we're probably not going to have time to actually look at the code itself, but it basically flows roughly along the slides. So if you guys are interested in looking at the code and playing along with it as we talk, feel free to spin up a Jupyter notebook and execute the code as we go along. So let's get started. So let's just talk about a simple example of control flow. So we got a simple graph, and we want to run either B or C depending on the result of A. So how might we do this in TensorFlow? So a naive way to do this using Python is to use multiple session runs. So we run A, and then we use an if-else statement to say, well, if it's this, then we should run B. Otherwise, we should run C. But this is it's awkward, right? First of all, we're fetching a value from the graph only to immediately feed it back in, just so that we can keep the graph continuous, sort of. As well, this logic isn't actually represented in our graph. If we exported the graph def, for those of you familiar with that structure, you're not going to actually see this if-else statement. So we lose that integrity and structure. And we're doing session.run 3 times, which is inefficient, and we really only want to have to run session.run once per loop. It just makes sense. What we'd really like is some sort of native logic gate. Wouldn't that be nice? And the obvious follow-up is, we have that, hooray. So the types of control flow available in TensorFlow, we have dependencies, we have conditional statements, and we have while loops. So we're going to be talking about all 3 of these today. Just by a random show of hands, before today, who knew that there were control flow, if-else statements, while loops, things like that in TensorFlow? Okay, how many of you guys have used those things in your code before? Okay, so less and then even less. So we're going to be talking about these. These are actually not very difficult to use, and they're going to make your code much more powerful, and it's going to enable you to see way more possibilities in your code. So why do we care about native control flow? 3 reasons I'm listing here. We have efficiency, we have flexibility, and then we have compatibility. So efficiency. Passing data to and from the Python layer is slow. People generally know this. It's getting better, but people recommend using TensorFlow queues. But if we have to pass data back and forth between the Python layer and the C++ layer, it's going to be inefficient. We want to be able to run the graph end to end as much as we can. That is, we want to just be able to call session.run once and then have the code completely go through the C++ layer. Again, it allows us to take advantage of built-in pipelining such as queues. For flexibility, it allows us to empower our static graphs with dynamic components. So one of the things that people like using Torch over TensorFlow for is the fact that it uses dynamic graphs. That is, you can change the graph at runtime. TensorFlow, because of its capacity for deployment, is required. It has this static graph requirement. But that doesn't mean that we can't have dynamics. We can't have a dynamic graph even though it's statically defined. We are able to keep all of our graph logic in one place, which leads to better decoupling. So that means that we can change our graph without having to affect the training loop. The entire graph has all of the logic it needs. We can take that out, spit it out somewhere else. We can change the graph, and we can still have our same training loop. And then compatibility. We can debug and inspect our code, our graphs with TensorBoard. We can deploy with TensorFlow serving using these operations. And we can use auto-differentiation, queues, and pipelining. And just as a quick note, I'm not good with colors, so we're going to be switching back and forth between blue and green, or orange and blue, sorry. So here we are in orange. And first up, we're going to be talking about control dependencies. So just a quick recap on dependencies for those of you guys who aren't fresh on your graph structure. So we have a graph. Here it is. And we've got nodes, which are the circles. These represent our operations in TensorFlow. And then we have our edges, the arrows, which represent the actual numeric tensor data. Dependencies are the nodes required to compute another node, right? So for the last node, the node on the far right, the dependencies of it are all of the other nodes, because in order to compute it, we need all of those other all of the other nodes. We need to compute all of them. If we're going to do the dependency for the top purple node, we get just that top green node. So dependencies in execution order. TensorFlow keeps track of every single operation's dependencies. And it uses them to schedule your computation. That is, there's basically a pool or a bag of operations that are eligible to run. And as soon as an operation's dependencies have all completed, it's thrown into that bag and is eligible to be run and scheduled by the TensorFlow runtime. That means any two eligible ops, two operations that have all of their dependencies complete, can be run in any order. So if we go back to our graph, the first two nodes have no dependencies, which means they can run in either order. The top one might run first or the bottom one might run first. Often, that's not an issue. But there are situations where we have a race condition. So this is a rather contrived example, but it shows us what might happen. So the bottom node is writing to the variable. It's saying, hey, I want to update the op in some way, shape, or form. But the top one is reading from that variable. It says, hey, I want to get the value of that node. So just to illustrate what we might have here, if we have a variable, we have the top node reading from it, and its output is 2 times whatever the variable's value is. The bottom one is assigning a value to the variable. It's saying, okay, take the variable, add 2 to it. And our output is the top plus the bottom. The problem is that this causes non-deterministic run situations. And I know this seems like, well, obviously that's non-deterministic. You shouldn't program like an idiot. This is a really simple situation, but it's important to note that this can happen in much more complex code, and it's important to know how to debug these sorts of situations once they start popping up in your code. So how do we prevent this? So we have operations that allow us to have more control over managing our dependencies. So by default, TensorFlow automatically determines the dependencies for each op. Basically, any op that is an input to an operation is a dependency. Makes sense. But we can also add additional dependencies that are not automatically defined by TensorFlow. And that forces those dependencies to run first. So that means we can control the order of how this graph runs by adding additional dependencies. So if we want the variable to change first, and then we read from it, we add the bottom node as a dependency to the top node. So the dependency runs first. So in this case, the bottom node runs first, and then the top node. We can flip it to make it so that we read from the node first, before we actually change that variable. So the way we do this, the standard way to do this, is by using tf.controlDependencies, which is just a standard operation in TensorFlow. All we need to do is add a with tf.controlDependencies, and then the list of all the operations that we'd like to add as dependencies. In this situation, we're only adding a single node. We still have to place it in list braces. But notice with this line, we're saying, hey, bottom node, you have to wait for the top node to finish. Okay? So what I just said on that slide. So use cases for adjusting and playing with our control dependencies. We can enforce execution order, which is what we just talked about. We can also group operations together. So we can run many operations with one helper. We can also add assertion statements for debugging purposes. So let's look at grouping. So now we have many variables that are all writing to, each operation is writing to a separate variable. And the goal is that we want to be able to run all of these ops every run or every so often. The scenario that you might see this in is something like the dueling double queue networks, like Ilya just talked about. Basically, every so often you need to transfer variables from the online network to the target network. And so we have all these variables that we need to transfer values over to and from. But passing in a bunch of operations to session.run is a pain. And if we change the number of operations that we're updating, then we have to all of a sudden change our session.run call, and that's just really obnoxious. What we can do instead is add a helper operation that has all of these operations as dependencies, basically saying, in order for this node to run, all of these other like individual update ops must run first. So that's, if we do this, this will give us a much simpler code where we basically have an update all op, and then we don't care what the output of it is. And we can change the number of dependencies, we can change the number of update ops, and thus the number of dependencies, and we still have the same session.run call. So the raw way to group these operations together is to somehow have a list of these update operations. You might have a for loop that iterates over all your update operations, however you want to do it. But then we end up by just saying, okay, with tf.control dependencies, list of all of my update operations, please give me this update all operation. And tf.noop is exactly what it sounds like. It doesn't do anything. It's just a blank operation that's used for helpers. But this is actually a common enough pattern that TensorFlow has a helper for this to make it just a little bit cleaner. We have tf.group. So we have tf.group, and it expects asterisk args amount of arguments, so you have to use the asterisk argument to unpack the list. But it uses tf.control dependencies under the hood, but also has some extra helpers, such as keeping all of the operations that are placed on a certain GPU on that GPU. So it's actually a really nice way to do this exact pattern. So another situation that might pop up, we have assertions. So we have a graph, and we need to validate that the tensor going into the blue operation is valid. We're just saying, okay, this is a likely scenario where something might go haywire, and we want to be able to check for this at runtime. So one way you might do this is, again, have a session.run and output a check me value, and then if it doesn't pass the validation, we raise some sort of error. But again, this is a pain in the butt, and the more assertions you need to make, the more changes you need to make, and it'd be way more fun, it'd be way better if we could validate as the graph goes along. Luckily, we can do that. There's a function called tf.assert. Actually, it's capital A. Apologies for the mix-up there. But tf.assert raises an exception if the value you pass into it returns false. So we can then make that assertion statement a dependency in order to force it to run. Unfortunately, assert doesn't return anything, and there's no sort of meaningful way to pass it into an op. So by using control dependencies, you can force it to run along, like before another operation, a critical op runs. So the way we do this is we have some assert op. We are saying, we are asserting that check me is not equal to 0. We're preventing it from being equal to 0 before running this divide operation. In such a way, we're preventing it from dividing by 0. So this is obviously a very simple example, but I want you guys to see that it's totally possible to add debugging assertions into your graph directly. So there's the required arguments for tf.assert. We need the Boolean check value. It needs to be a scalar Boolean, just a true or false. It can be one of TensorFlow's built in, or you can use one of the helpers like I'm using here, some sugar. And then the check me is the tensor that prints out. So basically, when it breaks, it'll say, hey, this assertion failed, and here's the tensor output that you wanted me to look at. Basically saying, like, we failed, here's relevant information you might care about. And you'll see here, and it says, check me with 0. That's not right. So another common scenario using built-in helpers, if you have not a number infinity because of exploding gradients or something like that, you can use tf.checkNumerics to automatically sort of put together this assert statement for you. You still have to add the control dependencies operation at the beginning. So there's lots of built-in assertion helpers, and I've added some links to the code down here. Again, I have these slides here, so you don't need to try to read the tiny text. So one last quick example for these. There's synchronization. If we need to wait for both of these to finish before moving on, but they're not on the same dependency graph, we can use tf.tuple to force them to wait for one another. So we have some operation that we're waiting for, and we have another operation that we're waiting for, and then tf.tuple basically says, okay, we're going to keep these operations separate, but we'll wait for them. We're going to wait for both of them to finish before passing them on. That said, TensorFlow already waits for dependencies, so tf.tuple is usually saved for unique requirements, things like big distributed training or multi-GPU training, where even though operations might be able to run asynchronously, you want to enforce this sort of synchronization directly. So that's it for control dependencies. Next up on the blue slides, we're looking at some conditional logic. So the idea is we want to be able to run different operations based on intermediate results. So basically the first example that I mentioned at the beginning of this talk. So TensorFlow offers two primary ops for conditionals. We have tf.condition or tf.cond, which acts like an if-else statement, and then tf.case, which is like a case statement in non-Python languages. So let's talk about tf.cond first. So it takes in 3 inputs, 3 required arguments. The first is a scalar Boolean predicate, so basically is the switch statement. The switch statement that tells TensorFlow which which operations we should run. The run if true is a callable, a function, a lambda, a functor if you're one of those people. But basically, we aren't passing in an operation. We're not passing in like the result of a function. You don't want to add your parentheses. We're adding in a lambda, something that can be called later on inside the function. And we'll show some examples. It should not take any input, and it should return 0 or more tensors. And then this is the path that will run if the predicate is true. In the documentation, it's not called run if true. It's called fn1, which isn't particularly semantic, so I changed it here for the talk. The other one is similar, but it is the false path, right? It's very similar. It runs if the predicate is false. So just a quick example. Here we have our predicate of A is less than B. Our run if true statement is please add together 3 plus 3. Our false statement is please square 3. And then our actual condition statement are these functions. Again, note that we're defining the function run if true and run if false, but we're not actually calling it. tf.cond runs it itself so that it can have those operations as part of its scope. So you might, for something as simple as what we did, you might do a simple one-liner instead. So the graph that we just made using this code would look like this. We have our A and our B inputs. Those get passed to a less than function. So is A less than B? That then gets passed to our conditional. And the conditional has links to both the run if true graph as well as the run if false graph. And it decides whether or not to run one or the other based on the Boolean input. And just a couple quick notes on the cond. Both of the callables must have the same return signature. So they both have to have the same number of tensors and the same type of tensors. TensorFlow doesn't make any checks on the size, I don't believe. I might be wrong, but just know that they should be the same. Both should return the same value. And then external ops needed for either branch will always run. So if we had the run if false section use some operation that run if true side doesn't, the operation that the run if false side needs will always run even if we're not running that branch. So the end result of that is try to place as many operations that are exclusive to one branch as possible. So now to move on to our next operation, we have a situation where instead of just two operations, or two possibilities, we have a list of operations that we may need to run depending on the scenario. So we have either a list of if-else statements, or if we're using switch statement, we have a bunch of cases and a default option. So instead of chaining tf.cond over and over again, which you can do, you can instead use a single tf.case statement. So tf.case is similar in some ways, but it's slightly different just because we're dealing with a variable number of possibilities. So it has two required arguments. The first is the predicate function pairs. It's a list of tuple pairs, where the first entry is the predicate Boolean value, true or false, single scalar, and the second is that callable function that we want to run. And then it can also be a dictionary if you prefer. I don't know if there's a settled preference on this yet, but you can use either a pair, like a tuple, a predicate callable, or you can use a dictionary where the key is the callable operation and the true or false Boolean operation, and the key is the callable function. It also takes in a default operation, and this is just callable, and it's what happens if none of the other predicates are true. It's just a default value. So just as a basic example of this, we're going to define our A, B, and C pairs, where we have if the previous value is less than 0, we run the first function, less than 10, we run B, less than 20, we run C. We put those as our predicate function pairs. And then we have a default value where it says if none of those are true, then please run this operation instead. And then our final case statement is this. So a few notes on tf.cond. All of the callables return signatures have to match, just like tf.cond. Yeah. Oh, sorry, tf.case notes, apologies. So only one callable will run, as if each case had a break statement, so you're not going to have this sort of waterfall effect where, oh, the second one ran, and so now we're going to run all the bottom. We're only running one branch exclusively. And then there's also an optional parameter called exclusive, and it defaults to false. If you set it to true, it basically checks to make sure that only one of the predicate pairs is true. If multiple of them are true, it throws up an exception. So it's another way to do some checking if you know for certain that there's no way that two operations should be set to true. And then just a few quick general notes on using conditional logic. Ops on non-selected branches are not run, which means it's great if you can avoid heavy computation on one path. So an example of this is stochastic depth, if you guys have heard of that. In the notebook, I included some example demo functions showcasing stochastic depth, how you might implement that in TensorFlow in a sort of lightweight way, and then showcasing the performance increases that you get from that. Basically, if you haven't heard of stochastic depth, it's like dropout, but instead of dropping out neurons, you're dropping out entire layers. And then also TensorFlow is able to differentiate through the selected path. So even if it's able to know that and say, okay, I didn't go through this path, the derivative for each of these should be set to zero because we didn't use those nodes. And then just as a TensorBoard specific note, when you're viewing these things in TensorBoard, the logic can get ugly. It doesn't by default add a name scope to each case statement, and it doesn't or add one to the true side or the false side. So make sure that you add a variable scope or a name scope in order to keep that clean in TensorFlow inside of your callable functions. Cool. So that's conditionals. So now let's finish up with some while loops. So common uses of while loops in TensorFlow, feeding intermediate results back into your graph, so RNNE sorts of things, or unrolling a loop of operations. There we go. So just an example of feeding results back into the graph itself. Basically, we have one operation or some like set operation. We have some starting value, and then we loop over and over again, feeding values back into the end result back into itself until we finished our loops and we're happy with the final end result. That's one way we might do it using Python loops. But notice that, so basically we're doing exactly that, and that graph looks like this. The problem is that this loop happens in the Python layer, which means that we're constantly going out of the C++ layer, feeding data back to Python, and then feeding that data back down through the swig pipeline into C++, which is inefficient. Or we might see unruling loops of operations. That is basically recreating the same type of op over and over again in order to have this repeating effect, and basically create a bunch of ops in the graph. So the physical graph for that would look like this. Bunch of nodes going from left to right. The thing is, every op that you add adds additional overhead. Unfortunately, there is just overhead from having data transferred from node to node, even in the C++ layer, and it takes more time in order to actually create the graph in TensorFlow. So ideally, we have a C++ layer loop that's able to have fewer ops added to the graph. And that's exactly what tf.while loop is for. So basically, tf.while loop takes in 3 required arguments. We're going to start from the back first and then move forward, just because tf.while loop might not behave exactly the way you expect it to. Maybe it performs exactly the way you think it is, but just I think to make it a little bit more clear, we're going to talk about the loop variables first before moving on to the first 2 arguments. So what the loop variables argument is it is a list or tuple of tensors that are used as inputs to the first iteration of the while loop. So the documentation doesn't make it super clear that this is like the first iteration input. But so basically you're going to have a counter if you have this, as well as the inputs to the meat body. So these inputs are passed to both the condition and the body. So you're going to have both your counter as well as your body inputs in the loop variables. Now to the callable cond in body. So again, it maps from whatever our loop variables are, the number of inputs, to a Boolean scalar. And as you'd expect, if it's true, then we actually execute the body. Otherwise, we exit the loop. Makes sense. Then the body is where our actual computation happens, and it maps from our current input loop variables to the next input loop variables. So the inputs to the next loop are the outputs from the body. So that's something that I think takes some people by surprise a little bit, but it's just something to note that your incrementation needs to happen in the body. It doesn't happen outside using some magic. Just increment it all in the body, and both the inputs to condition and body are the same. So again, main computation takes place in the body, and you need to increment the counter if you're doing loops like that here. So output from this gets sent to the next iteration of condition and body. Just graphically, going over what this looks like, we have some loop. We take our initial loop variables and pass those in, and those become the loop variables, the active loop variables. Those get passed to the condition, which then checks to see whether or not it's true or not. If it is true, the loop variables then get sent to the body. The body does its computation, and now the loop variables are the output from the body. And then this process repeats so long as condition evaluates to true. Makes sense, it's a while loop. Then finally, once we're done, we return the current loop variables. And just to note, while loop is totally compatible with automatic differentiation. So if you have it loop 10 times, it's going to automatically differentiate backwards 10 times. And here's an example of doing a very, very, very simple while loop 100 times. All we're doing is adding +5 100 times. So we have our condition, which takes in our index or I, as well as the value that we're not using. And it's just saying, hey, well, I is less than 100. Our body is saying, okay, we're going to take in I and val. We're going to increment I here, as well as adding up our val. We could be doing any number of operations here. We could be doing matrix multiplications, but just to illustrate, writing 5. And then we create our loop, where we have our condition and body defined above, and then we give it our starter parameters. These are just going to turn into tf.constant 0 just as a helper, but we're just saying, okay, we're going to start it off with I equal to 0 and initial val equal to 0. Again, note that condition and body take the same inputs, and that the body returns those same parameters, and they match up. And reusing variables is easy, so you can just use tf.getVariable, and it'll be able to take care of it. You don't have to worry about using scope.reuse variables because it actually only creates those operations once. It only calls these functions once under the hood. So you're fine just calling tf.getVariable. And then, again, once you're reusing variables and feeding data back into yourself, you have basically what an RNN is. And tf.dynamic RNN is implemented with a tf.while loop. So I don't have a full, robust implementation of dynamic RNN for you. That's on the TensorFlow GitHub repo. I do have a very simple RNN implementation if you guys are interested in seeing what that might look like in the notebook. And then just a couple of optional parameters to a while loop. So we have shape invariance. This defaults to none. Basically, tf.while loop forces you to keep the same shape for each of the loop variables throughout the process. So that way you don't end up with shape like tensors that don't align with one another. If you know for a fact that certain parameters are going to be changing as you compute, you can use shape invariance to say, hey, I want this specific variable in the loop vars to be able to have a variable, a dimension 2. Just letting you know, dimension 2 might change for this guy. There's also parallel iterations. So it basically says if you have an operation or a body function that can run in parallel, this is the maximum number of iterations that will run in parallel. And then swap memory. Because RNN, like long RNN backpropagation is really memory intensive, if you set swap memory to true, this will allow you to actually swap memory back from the GPU and the CPU. It's slow to do that, but if you don't have a GPU with a lot of memory, you might be able to use this to be able to actually run some models. And then finally, backprop allows you or disallows backpropagation for this loop. It doesn't make a huge deal, but if you're if you have a model that's pre-trained and you're just doing inference, you might get a few clicks of performance gain by setting this to false. And then finally, like just general purpose while loop notes. It's faster than refeeding with session.run. So just like by doing naive Python loops versus tf.while loop, you're going to get a 30% improvement by using while loop, roughly, more or less. It's much faster than unrolling and creating lots of ops instead of just using a while loop. It's going to be faster for graph creation, and it's going to be faster when running. And then, again, like with conditionals, the TensorFlow graph can get ugly, so it's important that you use name and variable scopes for your condition and body. And so now let's wrap this up. Today we just covered TensorFlow's main control flow ops. We talked about dependency management, conditional statements, and loops. And when you use native control flow, you minimize your overhead through from data transfer. Your graph logic is self-contained, and it enables the use of automatic differentiation and queues. So great. Thank you guys so much for listening. If you guys are interested in talking to me more, here's my contact information. I'm available to just have a chat, or if you guys want me for training or consultation, I'm available for you guys to do things like that, corporate and personal.